Hello students, in the previous lecture we have discussed about the dual behavior of a matter. Okay, dual behavior of matter, and in that we have seen the de Broglie relationship. Okay, and now we can see few more important points about the de Broglie's equation. Okay, so what is that important point is that according to the de Broglie, every object in motion has a wave character. Every object means you can take anyone, simply a ball or something like a stone or a bus or a scooter, any object in motion. Any object in motion has a wave character. Okay, so then you will get a doubt, right? Sir, the bus is moving, right? It is in motion. You are telling that it has a wave nature. So but we are not able to observing that wave character, right? Wave character of the bus. Are you observing when the bus is moving? Are you able to find that wave nature of that wave? How the bus is moving? Okay, have you find anything like that? I think I cannot. I cannot. Okay, but according to the de Broglie, what he is saying, every object in the motion has a wave character. Every object in the motion has a wave character. Okay, but he also gave some more conclusion that the wavelengths associated with the ordinary objects like a ball or stone or a bus or a scooter, whatever that is, with the high mass are so short, the wavelength for them that is very short, so that their wave properties cannot be detected. Their properties cannot be detected because their mass is very high. So that is the reason why the wavelengths are very short. Wavelengths are very short, because what is his relation? The relation is lambda is equal to h by mc. That means the lambda is reciprocal. Is it directly proportional to the mass? No, reciprocal. Okay, if the mass is more, the lambda is small. If the mass is less, the lambda is more. Okay, so what he said, if the mass is high, then the lambda is very short, so that you cannot detect. But when you come to the wavelengths associated with the electrons, because the electrons has a very less mass. It has a very small mass. Okay, and that is the reason why with the electrons and subatomic particles can be detected experimentally. The wavelength can be detected experimentally and valuable. Okay, so that means whatever that particles or object or matter with the high mass, the wavelengths are very small, so that they can be neglected. But when you come to the matter with the very small mass, okay, very small mass, that can be, the wavelengths can be detected and are valuable Okay, now your doubt is clear, right? So the bus mass is very high, so that we cannot detect the wavelength. Of course it has, but it is very small, so that it is negligible. Okay, then these sentences again we can confirm by seeing two problems. What are the problems in the textbook? The problem 1.12, another one is the 1.13. Okay, so what is the problem 1.12? What will be the wavelength of a ball of mass 0.1 kg moving with the velocity of 10 meters per second? Okay, what he is asking, what will be the wavelength of a ball? Okay, ball with the mass of 0.1 kg and it is moving with the velocity of 10 meters per second. Okay, that is fine. And one more problem, the mass of an electron is 9.1 into 10 to the power of minus 31 kg. If its kinetic energy is 3.0 into 10 to the power of minus 25 joules. Calculate its wavelength. Okay, so instead of the velocity, he has given the kinetic energy. So you know that you can easily calculate the velocity by using the kinetic energy. What is the kinetic energy? It is half mv square. So the v is equal to obviously 2 ke divided by m to the power of 1 by 2. To the power of 1 by 2. So with that you can get the velocity. Okay, so then what is the difference between these two problems? Both are same. It looks same, but what is the difference? Only the mass of the matter. So here the matter is a ball and mass is 0.1 kg. You see, but here the matter is an electron and its mass is very small. Its mass is very small. Okay, so okay, then we can calculate the wavelength for both. So first, according to the de Broglie, you know that the lambda wavelength is equal to h by mv, and what is the h? 6.626 into 10 to the power of minus 34 joule second divided by mass is 0.1 kg and velocity is 10 meter per second. So when you substitute, you can get a value 6.626 into 10 to the power of minus 34 meters. Okay, you see the value, it is in 10 to the power of minus, in the 10 to the power of minus 34 meters. Okay, so here come to the units. How you have to remove the units is that above joule per second is there, right? Above joule second is there, not per second, divided by, and downside there is a kg into meter second inverse is there. Okay, so how you will remove these? You know the joule is equal, what is the joule? The joule is equal to kg meter square per second, second to the power of minus 2. What is the joule? The kg, substitute this, meter square second minus 2 into what is that? The next there is a second divided by again kg into meter per second. Okay, so second, and there is a 1 and a second inverse and a meter kg. So finally what you will get? You will get only the meters. Okay, the lambda you will take in the meters. The wavelength you will consider it is in the meters. Okay, so the value here. Okay, and the next one is that the mass of an electron. Okay, in this problem what you have to do, you have to first find out the velocity. So the velocity is equal to 2 into kinetic energy divided by mass to the power of 1 by 2. So you will get the 812 meter per second. The velocity is 812 meter per second. Then substitute this velocity in the de Broglie. What is that? The h del lambda is equal to h by mv. The h is equal to the 6.626 into 10 to the power of minus 34 joule second, and the mass is equal 9.1 into 10 to the power of minus 13 kg, and it is 812 meter second inverse. 812 meter second inverse. So when you calculate all these things, minus 31, minus 34, so that minus 3 will be there. Okay, so when you do it, you will get a value of 8967 into 10 to the power of minus 10 meters. Or else simply you can write 8.967 into 10 to the power of minus 7 meters. Or you convert that into the nanometers. Okay, how you will convert that nanometers? Okay, before the conversion, you see the comparison. So earlier in the problem, with the high mass for a ball, what is the lambda? It is 6.626 into 10 to the power of minus 34. But come to the electron, the lambda is only about 9 into 10 to the power of minus 7. Right? Here it is in the 10 to the power of minus 7. Here it is in the 10 to the power of minus 34. Right? So which one has a very less value? Obviously the first one. And it has a considerable value. Okay, so that is the reason why generally the objects, the matter with the very less mass, we will consider the wavelength. Okay, but when you come to the high mass objects or matter, the wavelengths cannot be considered. The wavelengths cannot be considered. Okay. Now come to the conversion. Here meters you are converting into the nanometers. Okay. So I will convert very simple. 1 nanometer is equal, do you know the nano? What is that? 10 to the power of minus 9 meters. Or simply 1 meter is equal to, we come here 10 to the power of 9 nanometers. Okay, and there is a one more unit, it is going to become that 1 angstrom is equal to 1 angstrom is equal to 10 to the power of minus 10 meters, or simply 1 meter is equal 10 to the power of 10 angstroms. 10 to the power of 10 angstroms. Okay, these are very, very important. You have to be know, right? So this is all about the de Broglie's dual behavior of matter. Okay, so with this, finally what we are going to be conclude is that the de Broglie equation gives the relation between the wavelength and the momentum or momentum. Okay, that is the lambda is equal to h by rho. Okay, and the de Broglie equation in the when the de Broglie's equation implied, so the wavelengths associated with the ordinary objects we cannot find out because those are very, very small. Okay, but come to the small particles like subatomic particles, you can find out the lambda values, wavelength values, and are considerable. Okay, and there is a one more problem. We can see the back side. This less. So what is the problem? 1.14, that is calculate the mass of a photon with wavelength 3.6 angstroms. So what you have to do, you have to calculate the mass of a photon with the wavelength of 3.6 angstroms. Okay, very simple. According to the de Broglie, the lambda is equal, sorry, what is that? The lambda is equal to h by mv. Okay, and you know the lambda here, wavelength, right? And you have to calculate the mass. For that, what you required? H, you know already, Planck's constant, and the velocity. Velocity of the photons, you know that velocity of the light always same. Photon is nothing but electromagnetic radiation. So that is the velocity of photon is equal velocity of the light. Okay, substitute the v value 3.6 into 10 to the power of minus, sorry. So the velocity of the light, how much it is? 3 into 10 to the power of 8 meter per second. 3.3 into 10 to the power of 8 meter per second. Okay, and come to the lambda, that is m is equal to h by lambda v. What is the lambda? 3.6 angstroms, and convert into the meters. Just you have to multiply with the 10 to the power of minus 10. That's it. Okay, and when you multiply that, you can get a value. The mass it is 6.3135 into 10 to the power of minus 33 kg. Okay, so this is all about the problem, and in the next class we are going to see the another important topic, that is Heisenberg uncertainty principle. Okay.